So in this video, we're going to look at what actually pushes current. So why is it that current flows at all? That's because of a potential difference. So potential difference is the thing that pushes current or makes charges move down the wire. The symbol for potential difference is delta V, and its units are similar but not the same. Its units are volts. So the symbol is delta V. The units here are the volt. And that gives rise to another name for potential difference, which you may have heard of. That's the voltage. So the voltage and the potential difference are the same thing. Potential difference is an amount of energy. So it's related to a joule, but it's an amount of energy that a charge carries. So it's an amount of energy per coulomb. So it's I'll just write this on the side here. It's a joule per coulomb. So it's how much energy a single charge is carrying through the circuit. Because we want to think about it as this, we really want to think about it as a potential energy difference. That's a really helpful way to think about voltage. So a really nice analogy is to think about voltage as a height. We've been talking about in our last unit gravitational potential energy, right? And gravitational potential energy goes up as you go higher. So if you're higher up, you have more energy or more ability to do work. And the same thing is true with voltage. So a higher height is like a higher voltage. And if you have a bigger drop in height, you have a bigger difference in voltage, or a bigger potential difference is essentially the same thing. So a battery, think about when charge goes through a battery, think about it as like going up an escalator, like it's going up the stairs from a low voltage to a higher voltage at the other end of the battery. So battery has this potential difference where delta V, so that's really what we're interested in with the voltage, is V2 minus V1. And that V2 end is going to be higher than the V1. So that gives you a positive voltage or going up in height. If we think about this in our analogy of say, water, we said that current was how much water is flowing past a point in the river per second. Well, what pushes that water? What makes it move? It's a height difference in the terrain, right? So a waterfall is a really obvious height difference. Where the reason why all this current of water is flowing is because you have this big height difference in your terrain, and that pushes the water. It's this gravitational potential energy that's pushing the water down the waterfall. So think about voltage in the same way as a waterfall. All right, so we said it's really connected to energy, and it is. So the difference in electrical potential energy. So this right here is the electrical potential energy difference. So an E for energy, Q for electrical energy, is actually the charge. So this here is electrical potential energy. So that's what that variable is here, but that's equal to the charge. So Q is the charge multiplied by that voltage. Delta V is your voltage or your electrical potential difference. Let's look at that in an actual problem. So say you've got a 12-volt battery. So if I see the units of volts, that means that I'm talking about a potential difference. So 12 volts there. It causes 2.25 amps of current to flow. So the current, the symbol for that is I. So 2.25 amps to flow around the circuit. And the time that's going to go by is 3 minutes. Now I need to convert that into seconds. So you're going to want to multiply by 60 seconds over 1 minute. And what we get there when we do 3 times 60 is 180 seconds. If I plug all of this into my equation here, I have the change in electrical potential energy is going to be Q times delta V. Now the problem is it looks like I don't know Q here, right? But I actually do, because we remember this lovely equation that current is how much charge flows per second. So I could rearrange this for Q by multiplying both sides by delta T. So if I do that, multiply this side by delta T and this side by delta T, that cancels off my delta T's here. And I get a nice equation for charge, which is current times delta T. And I can take that equation for charge and sub it right in here. So what I get is my change in electrical energy is charge, which is actually current times time times my electrical potential difference. Plug all your numbers in. We have 2.25 amps here, 180 seconds, and 12 volts there. If you toss that all in, we get electrical potential energy of 4.86 times 10 to the 3 joules. And then we should watch out for our sig figs there. It looks like 3 sig figs everywhere. So we're good. And that is our change in electrical potential energy from that battery.